Welcome to this lecture series in linear algebra. In this lecture, we'll look at an application of what we have done, and it will be about the Fibonacci sequence and the general formula for it. So let us recall. So for a endomorphism T on a finite dimensional vector space V or a base field F, we know that T is diagonalizable if and only if the minimal polynomial of T splits into distinct linear factors, of course, over the base field. So this is basically what we need to know, and in some sense we don't even need to know that. But anyway, here is a problem which is star marked, not because it is hard, but because we are going to use it. Well, technically we don't really need this problem either, but still, it's a problem which is interesting in its own right, and it does help. Okay. So the Fibonacci sequence, I'm sure you know about this. YouTube has blown this out of proportion anyway. So suppose we have these two numbers, 0 and 1, and the next number we produce is the sum of these two. And the next number we'll produce is the sum of the previous two. So the next number in this sequence would be 2. And now the next number would be 2 plus 1. So it's 3. And then the next number is 2 plus 3, and this will go like this. So this is 5, and then 8, 13, and so on. So that's the Fibonacci sequence, and it's unclear as to what should be the general formula for such a thing. So this is what we will denote as F0. This is F1. This is F2. And so on. So what we want to ask is, can we write down a general formula for Fn? And if I were faced with this problem for the first time, I would think that this is such an erratic sequence that there may be no closed form solution to this. It is a well-defined sequence, but how would you find out a general formula? Turns out there's a very general technique to find out the general formula. And this is a small illustration of that technique. I find this proof really beautiful, and even the formula is quite surprising. So here is the formula. The nth term is, this horrible looking thing, and why should irrationals appear here is a mystery as of now. But the proof that we are going to write down will reveal that mystery completely. So here is the proof. We will use linear algebra. So define a map T from R2 to R2 as T of x comma y is y comma x plus y. So this is a map, and of course this is a linear map. So note that T is linear. Okay, so it's an R linear map. When I say linear, of course, this is a vector space over R. So we have a linear map, and note, more importantly, that T of this pair f of fn minus 2 comma fn minus 1, this is what? This is equal to fn minus 1 comma fn minus 2 plus fn minus 1. And what is this? This is equal to, this is for all n greater than equal to 2. Right, so the way Fibonacci sequence was defined, we have this sum is equal to that, because the nth Fibonacci term is the sum of the previous two terms. So maybe I should have written it here, but anyway. So this is an important observation, that this becomes that under one iterate of T. And therefore, one can easily prove that. Main observation is that the nth iterate of this vector is this. So you start with f0 comma f1, apply t to it, you will get f1 or no, you will get what? So you will get f1 comma f2, which is correct, because what you will get is 1 comma 2, and that's what. So you can just check this and prove this via induction if you like. So this is the main observation, that just the nth hit from t to this vector gives you, the first coordinate of it gives you the nth term of the Fibonacci sequence. So can we somehow find this out? And yes, we can. So first of all, so let me use a different page. So first we claim that t has two distinct eigenvalues. This I'm sure you can prove yourself, but I'll give a full proof. You can, if I ask you to find the eigenvalues, you should be able to. So let's try to find the eigenvalues. So let lambda be in R and W be this vector in R2. And I insist that it is a non-zero vector. Maybe I should write 0, 0. Doesn't matter. Be such that TW equals lambda W. Right? So let's try to find out what are the possibilities for lambda. So thus, TW equals beta comma alpha plus beta by definition of T, which is equal to lambda alpha comma beta, because TW is lambda W, which is lambda alpha lambda beta. All right. So we get beta equals lambda alpha and alpha plus beta equals lambda beta. What did we do? We just compared the two coordinates. So this gives us alpha plus lambda alpha equals lambda square alpha. So if you just eliminate beta, just substitute beta as lambda alpha, you will get this equation. So this implies 1 plus lambda into alpha equals lambda square alpha. So if alpha were 0, well, then we can't say anything. But if alpha were 0, I think it will turn out that W is 0. So let's see. So suppose alpha were 0. So then what happens? Then beta would also be 0, right? Because beta is lambda alpha. So alpha is non-zero. Maybe I should write it here. Alpha is non-zero is a deduction of this statement. Because if alpha were 0, then beta would also be 0, and hence W would become 0, but W is chosen to be non-zero. So this implies 1 plus lambda equals lambda square, which implies lambda is one of two things. So either lambda is 1 plus root 5 by 2, or lambda is equal to 1 minus root 5 by 2. So this we will call phi, maybe. Let's see. What's the good notation? I think this is called the golden ratio or something, which is as glorified as the Fibonacci sequence on YouTube. So let's call this phi, and let's call this phi bar. Okay, so what have we done so far? So what we have shown so far is there are only two candidates for the eigenvalues of T. One is this candidate and the second is this candidate. We have not so far shown that these are eigenvalues. We have shown that only these can be eigenvalues. Let that distinction be very clear. But if we can find eigenvectors corresponding to these numbers, then of course these become eigenvalues, and we can. So one can check that if, so define U as 1 comma phi and V as 1 comma phi bar, then what is TU? TU is phi comma 1 plus phi, right? That's what tu is, which is equal to 1 plus root 5 by 2, comma, what is 1 plus phi? 1 plus phi is, unfortunately, it is 3 plus root 5 by 2. And I want to show that this is equal to phi times 1 comma phi. But is that true? Because, yeah, I think it is. Because what is phi square? Is this equal to phi square? So let's compute phi square. What is phi square? Phi square is 1 plus 5 plus 2 root 5 by 4, which is indeed 3 plus, yeah, so that's fine. So just check that tu is equal to phi times 1 comma phi. It's just a matter of computation. And tv, maybe I'll write it here. tv is equal to phi bar comma 1, phi bar times 1 comma phi bar, which is phi bar v, and yeah, so I should have written this is equal to phi u. So the upshot is, indeed, phi and phi bar are the two eigenvalues. We cannot have more eigenvalues because eigenvectors corresponding to distinct eigenvalues are linearly independent. We cannot have more than two eigenvalues anyway, although that was also clear from this argument. And we have found the corresponding set of corresponding eigenvectors. So the upshot of this exercise is that just remember this guy. So remember these two things. And remember this fact that tu is phi u and tv is phi bar v. Okay, now we will proceed. So we want to find the nth iterate of 0, 1. So we will express 0, 1 as a linear combination of u and v, and let's say this is equal to alpha u plus beta v. We want to find alpha and beta, and do not confuse this alpha and this beta with the alpha and beta on the previous page. It's used in a different capacity. So yeah, so let's try to find out these alpha and beta, and what this implies is that 0, 1 is equal to alpha, alpha phi plus beta, beta phi bar, which is equal to alpha plus beta, alpha phi plus beta phi bar, which implies 0 is alpha plus beta, and 1 is alpha phi plus beta phi bar. And if you just compute this out, I have pre-computed this. If you compute this out, you will get that alpha is 1 upon root 5 and beta is minus 1 upon root 5. So that's something that you can verify. And therefore 0, 1, this vector is 1 upon root 5 u minus 1 upon root 5 v. So I can just write it like this. Okay, so what is t of this guy? This is tu minus tv equals 1 upon root 5 phi u minus phi bar v, right? And more generally, if you just keep iterating, this is equal to 1 upon root 5 phi to the n u minus phi bar to the n v. Okay, and what we are interested in, so as we wrote earlier, this guy is f sub n comma f sub n plus 1. I hope that is what we wrote. Yeah, so we have this, and therefore if we can just extract out the first coordinate of this guy, we will be done. But the first coordinate of this guy is very easy to write down because we know what is u. U is 1 comma something and v is also 1 comma something. So it says that f of n is 1 upon root 5 phi to the n minus phi bar to the n, because we are only interested in the first coordinate, and here we have a 1 in the first coordinate, so phi n comes here and phi bar n comes here with a minus sign, and that's it. So the expression for phi is precisely what you see here, basically. This is phi and that is phi bar. So we have obtained what we wanted. Sorry for spending some time here, but you just needed to verify that this is indeed an eigenvector with eigenvalue phi, that's all. And similarly for v. Okay, so very nice application of diagonalizability in some sense. What we are really doing is using the fact that t is diagonalizable. But anyway, we kind of done it from the very, very basics. All right.